Figaro, Figaro, Figaro. Is that thing on? I don't sing very well, and it's a little embarrassing in public because I don't practice very much. And your chances of becoming a great contemporary Christian music artist, if you don't practice, aren't any better than you becoming a great scientist if you just watch these videos and don't try them at home. These laboratories are designed for you to download the written instructions linked at the blog, do the experiments yourselves at home, do the analysis as shown in the videos, prepare the figures and tables, and write a lab report with a discussion explaining whether or not the hypothesis was supported and answering the other questions that are mentioned in the discussion section of the write-up. Thanks for joining us today at Carmel Academy. I'm Dr. Courtney, and today's experiment is about whether or not the ball velocity is proportional to the ramp height. And so the experimental design is simply to roll a ball down a ramp and to use the video program tracker to measure its velocity, not as it's rolling down the ramp because it's accelerating down the ramp, but once it reaches the level table, its velocity is approximately constant or constant enough. So the question is that constant velocity, once it gets to the level portion, proportional to the height from which it started? And we mean the starting height. We don't really mean the height at the top, because you can start rolling the ball down at different heights along the ramp. So, why is our hypothesis of proportionality? Well, the hypothesis of proportionality worked really well in the relationship between mass and volume experiment that we did a little while ago. The hypothesis of proportionality was also supported in our version of the ball drop experiment. So, hey, it seems like it's a good idea. We might test it. We might float it for this experiment also and see whether or not it's true. Alright, so the dependent variable is the velocity once you get to the bottom. The independent variable is the height of the ramp from which we started, and on our ramp here, and this is just a metal plate. And when we were piloting this experiment, we tried different things. We ended up settling on a metal plate because it was a little thinner than some of the wooden boards we tried. The little drop off at the bottom end of wooden boards, when you use those as ramps, unless you get a real thin one, kind of buggers up the experiment a little bit. So if you don't have something like a thin board or a thin metal plate, a lot of times a piece of cardboard can be carefully cut, is rigid enough to roll a small thing, this is a marble or a small ball down, and you can mark it. We have ours marked with some just little indexes made with a permanent marker, so we can start the ball rolling at different points. But we're actually using our video, as you'll see in the analysis portion, to determine both the initial height as well as the velocity, because the video can do it more accurately than we could pull out a ruler and measure the height off the table. Because what's really interesting is not the height up the ramp in this dimension, but it's the starting height relative to the surface of the table. So you'll see that when we set up our camera, we set it up at the same level, so we're truly looking edge on. The camera angle right now is looking a little bit down at things, so we set up, when we actually set up the video camera for the experimental part, we're looking perfectly edge on so that all the motion is in the same plane, so we can catch the initial height, and the tracker program can tell us that from the video, and the tracker program can also tell us the amount of time it takes to span a certain distance, and the 5-inch wide index card is in the background, both because it provides nice contrast for the marble, as well as because it's exactly 5 inches wide, and then we convert that to centimeters for the scale in the video. Okay, well, before we begin analyzing in the tracker program, let's simply play the video in a regular player at normal speed. So you can see that the ball is being released from a ramp multiple times, and that there's some care taken so that the camera angle gives the ramp edge on, so it's not looking down at the ramp and it's not looking up at the ramp. So all the motion is in a plane perpendicular to the camera. Further, note that some care is taken with the release so that the hand isn't blocking the bottom edge of the marble. So all we've done so far is open the video in Tracker for analysis, and as usual in Tracker, the first two steps are to set up a coordinate axis. So we'll drag the coordinate axis down toward here, because we're going to make the bottom left edge of the card the origin. You could really put the origin anywhere, but there's always a more convenient and a less convenient place to put it in problems involving motion, and the bottom left edge of the card just happens to be a fairly convenient place to put it. And if you notice, we have the coordinate system pretty well leveled just from leveling the camera carefully before making the video, but there's a slight discrepancies, so we can adjust the angle of the horizontal. Maybe let's try half a degree, and by adjusting it half a degree, now we see that the coordinate system lines up very close to perfectly with the index card, having made that modification. So we're zoomed in 200%. Now let's zoom in 400%, both to set the calibration sticks as well as to check to see if there needs to be any adjustments to the position of the origin. And I don't think there need to be. That's pretty good. So let's go ahead and set up the calibration stick. New calibration stick, and then shift click will mark this end. And so let's go ahead. You don't have to put the calibration stick at the y equals 0 position. You can put it a little higher. So let's line it up close to the that rule on the index card. So shift click sets the left edge. Come over here to the right edge. Shift click sets the right edge. So now we have the calibration stick, and now we can enter the length of the calibration stick, which is 12.7 centimeters, and it prompts us to want to change the length unit to centimeters, and yes, we do. So now we're ready to start rolling the video, and what we want is we want to get the last frame right before the marble's released, because that way we know there hasn't been any last second changes in height due to that hand that's holding it moving one way or the other. So that looks like it there. So let's go ahead, and I'm going to zoom into 400% just to try and get the initial position within a pixel. So now you can tell that it's getting the initial position really accurately there. And the initial position is y equals 1.462. So we'll write that in our lab notebook. So that's the height that the ball is going to start rolling from. And then we can come over here to the index card, because as we stop play, we want to stop motion, and we want to get it at the frame of motion where the ball just begins to come into the index card. And you'll notice there's kind of a blur, there's some pixelation and interleaving, but we want to recognize that that's all due to the imperfections in the camera. But if the ball, the leading edge, is really the position of the leading edge of the ball, the leading edge of the image, and the reason is the camera doesn't know where the ball is going to be in the future. It only knows where the ball has been. So the blur is due to the motion, but the leading edge is actually the accurate indication of the position of the ball. So we put the cursor there and we write down the position 0.770 centimeters. And let's go ahead, one convenient thing about trackers, you can reset the time to 0 early and often. So we're going to reset the initial time to 0 every time we analyze a trial. So every time the ball has just come onto the edge of the card, or the first frame where the ball is in front of the card, we're going to call that t equals 0 every time. And then we're going to move forward a number of frames until the last frame where the ball is in front of the card. Alright, so now let's move past the card, so we back it up a frame. So this is the last frame where the ball is in front of the index card. And I don't know how well you can see it on the video, but there are some pixels indicating the ball is there way out here. So this is the actual ball spread out due to the motion, and this is the shadow of the ball because the way the lighting was set up. Okay, so the time is 0.267, so that's the final time, and the final position we can see in yellow right there is 11.94 centimeters. Alright, so that completes the first trial from the first tick mark. Okay, so we stopped the motion right before the trial from the second tick mark. So let's go ahead and first we're going to zoom in 400% because we want to accurately determine the height of the bottom edge of the ball, which is a marble in this case. So zooming in, we can determine it to be right there rather accurately, and so the height is 2.725 centimeters. So write that in our lab notebook, and then we move forward. Let's go ahead and reposition the video so we can see it when it gets to the front of the card. And then we're just going to let it play and stop it when it gets to where it's in front of the card, and now we need to back it up just a few frames. So it's not quite in front of the card on that frame. So that's the first frame where the ball is in front of the card. So let's go ahead and set the time to 0 and determine the position, and that's the position of the leading edge as close as we can determine. It's 1.097, and then let's go ahead and find the other end of the card, and we're going to move it forward a few frames until we have the last frame where the ball is still in front of the card. And so that's the leading edge. So now the time is 0.200, and we can see that here. And the leading edge, we've set our cursor, and the leading edge is 12.35 centimeters. Okay, we've moved forward until the marble is at the third tick mark and the frame just before the marble gets released. So let's go ahead and zoom in to 400%, and then determine the position of the bottom edge of the marble is 4.017, and we're getting that number from here. This is the y coordinate at that point. And now we go ahead and readjust the video because we want to stop the motion when the ball gets to the in front of the index card. So ran a few frames past, so back it up a few frames. And so this looks like the frame where the marble just begins to be in front of the index card. So we set the time to 0. And we determine the X position out there at the leading edge to be 1.278. Now we reposition the frame so we can see the far edge of the index card, and we move forward until we have the last frame where the ball is in front of the index card, and we note that the time is 0.133 seconds and that the X position at this point is 10.85. So you can put the cursor in the right spot, pick off the position, 10.85 seconds. Okay, now we've found the frame right before the marble is released from the 4th tick mark. So we can go ahead and zoom in to 400%, find the bottom edge of the marble to establish the height, and that's 5.288 centimeters. And now we can move the frame over to the leading edge of the index card. Go ahead and play it. Stop it, back it up until the frame where the marble is just barely in front of the index card. And so that's it right there. The marble, the front edge of the marble is right there. So let's go ahead and set our 0 in time. So the time is 0 and the X position is 0.450. And let's go ahead and now pan over to the far edge and forward the video until we get the last frame that's in front of the video, in front of the index card rather. And so the time is 0.133, and now the time is here, and the X coordinate is 11.2 centimeters. Okay, so now we've moved forward to the last frame right before the marble is released from the 5th tick mark, and we want to zoom in to find the bottom of the marble as accurately as we can. So zoom in 400%, and the bottom of the marble is at a Y coordinate of 6.522 centimeters. And so now we can pan to the leading edge of the index card. Let the video play until the marble comes in front of the index card, and we move a little too far. The marble is moving a little faster now. There's more distance between frames. So this is the first frame where the marble's in front of the index card. We'll set the time to 0, and we'll come out here and identify the leading edge. And the leading edge is 1.868 centimeters. Now let's pan to the other edge of the index card and go forward a few frames. Oh, too far. So this looks like the last frame where the marble is in front of the index card. The time is 0.100, and you see the time here, and the X coordinate is 10.82. So now we have our table filled out in our lab notebook. So now this is the spreadsheet we have for analyzing our data in a spreadsheet. So you just enter it carefully, and so the initial height of the first tick mark is 1.462. The initial position was 0.770. The final position was 11.94. The initial 0, and the final time was 0.267. And so now you can see we've already set up the formula, and the formula from computing velocity is the change in position, x final minus x initial, divided by the change in time, which is time final minus time initial. So we have that set up here in a spreadsheet formula, and in this case it's element E5 minus D5, the difference in position, divided by element G5 minus F5, with the parentheses in the appropriate places. So it computed the velocity to be 41.8 centimeters per second. And this new column for the ratio, if you recall, our hypothesis was that the velocity would be proportional to the height. So in each row of the spreadsheet we're going to compute the ratio. So that's element C5 divided by element B5. Okay, so that completes the spreadsheet for the first row. The second row, the height was 2.725. The initial position was 1.097. The final position was 12.35, and the final time was 0.200. And copying and pasting the ratio formula shows that the ratio is closer to 21 than 28. Alright, after we complete the data entry, we see that the ratio seems to be decreasing markedly as the initial height of the ball increases. And so it doesn't look like our hypothesis is supported. So let's go ahead and look at this data a little differently. Let's copy the data and let's paste it into graph.exe to see what it looks like more visually. So we insert the point series, and let's go ahead and change our color to blue because I like blue. Blue is a color for the Air Force Academy. And let's call this ball ramp, and let's hit OK. Now we can't see because our zoom is all out of whack, but if we zoom fit, now we have our data. And now let's label our axes and take a little care. So the x-axis, the values of x run for the heights run from 0 to 6 and change, but let's go ahead and make 8 our maximum height. So let's label it height and make sure we put in our units of centimeters, and let's let it auto tick and auto grid because it usually makes pretty good choices. Alright, and now let's adjust our y-axis, because the y-axis had, this was our velocities. Let's go back to our spreadsheet here. So our velocities ran from up to about 89 centimeters per second. So why don't we graph from 0 to 100, and let's label the y-axis with velocity at the bottom of the ramp, and the units are centimeters per second. So now this is our raw data, and the reason I like to plot the origin is that a rough look might make you think, hey, well, this is a straight line, but the straight line wouldn't go through the origin. And we know that if we just set a ball on the table, that it would have 0 velocity because the initial height of a ball just set on the table is 0. So the ball needs to go through the origin, so we're going to enforce the idea that the ball goes through the origin when we do our trend line. So if we right click and insert a trend line, we force the vertical intercept to be 0, and so this is because we're testing a proportionality rather than just a linear relationship, and we see that that's not really a very good fit at all. The r squared is 0.46. The line doesn't really look like it's going through the data points very well. So let's go ahead and take a different approach. And one of the things I like to try, once you know it's not linear, but you know you go through the origin, is I often like to try a power law fit, because that can tell me what might be happening. So when you try a power law fit, we see a couple of things. We do see that the line or the curve very nearly goes through all the data points. We see that the r squared value is very close to 1.9966, and we also see an exponent that's close to a half. And having a little more experience at this, once you see an exponent that's close to the ratio of small integers, a half, 3/2, 2/3, you usually start thinking that maybe there might be a law of physics behind it that gives you an exponent that is the exact ratio of those two integers. So, and of course that's just the same as a square root function. So let's go ahead and try another trend line. And this time you can set up a user-defined function to be a square root, and what that is that's $A, and what the $A tells it is that that's going to be the variable or the adjustable parameter in the equation. So $A times the square root of x, and see what the fit comes out looking like when we tell it to fit to a square root function with one adjustable coefficient in front. So we can see that the adjustable parameter turns out to be 35 times the square root of x, and the r squared value is 0.996, so it's almost as good as the r squared value when we varied both the power and the coefficient in front. So this is suggestive that there's an underlying law of physics governing the motion of the ball down the ramp, that wants the relationship between the velocity and the height to go as the square root of the initial height rather than a proportionality as we had originally hypothesized. Alright, a few comments on this laboratory and an extended analysis if one intends to use it in a physics class rather than an 8th or 9th grade physical science class. I'm suggesting that there be multiple trials at every tick mark. So if you do multiple trials at every tick mark, this allows you to compute an average velocity and an average height for that tick mark, from which you can compute a standard deviation and the standard error. And you can then have 5 trials for every tick mark, and you can conduct a more extensive analysis. It takes a little more time and tracker, because now you've got 5 trials at every tick mark. But when you go through that more extensive analysis, because you have multiple trials, you end up with much better accuracy. So when you have the summary, which is now the average height and average velocity, you can also compute the errors or the uncertainties. So the uncertainty in height and velocity tend to end up a little better than 1% in most cases, a little worse than 1% in some cases, and then you can continue the analysis from there, but you have a higher level of accuracy that has its origin in the multiple trials at each tick mark. You probably also in a physics class want to talk about the underlying equations of conservation of energy that really govern this motion and lead to the observed behavior. Wow, that was an interesting and fun experiment, wasn't it? And it may have been a little surprising that in this case the hypothesis was not supported. That's why we do the experiments. If we knew in advance always what the outcome would be, there'd be no need for the scientific method and testing of hypotheses with experiments. And I also want to point out that not every mathematical relationship that pops up in the world of science is a straight line or exact proportionality, although a lot of them are, especially early on in your scientific career. So be on the lookout for other possibilities. Finally, I want to encourage you by letting you know that schoolwork is the work that God has given you to do, because God wants you to obey and to honor your father and mother. And insofar as your father and mother are telling you to apply yourself to your schoolwork and do your homework and try and learn what you're supposed to learn and try and earn good grades and so on, schoolwork is the work that God has given you. So, but I want to also encourage you with the Lord's Prayer, because where Jesus says in the Lord's Prayer, give us today our daily bread, part of that is success in your daily work. Because remember in Genesis, when man fell, part of God's redemptive discipline to man was that by the sweat of his brow, he would earn his bread. So there's this aspect where the fall of man has made work harder than it may have been had sin not entered the world through Adam. So part of the way to make that yoke lighter is simply to ask God for help as part of asking for your daily bread. Thanks for joining us today at Carmel Academy. I'm Dr. Courtney.